Welcome, everyone. So today we are going to talk about world persistent variables. Agenda. First of all, a quick definition of what are world persistent variables. I call them WPVs for short, as to differentiate them from PPVs, which are player persistent variables. How do you go about reading WPV values? Then there's some concurrency problems when people change WPVs in multiple instances simultaneously. It's something we don't have to worry about with PPVs, but with WPVs, definitely problems can ensue if you don't deal with the concurrency issues carefully. Then we're going to talk about two solutions to the concurrency problems. One of them is using counter increments, and the other is the object variable update, which uses optimistic locking in order to make sure that data isn't lost. And we'll talk about some best practices around that. And then I have two example mechanics that use WPVs. One is a limited run clothing sales, and the other one is a custom leaderboard. And the world that I will be showing is going to be available as a remixable world. So afterwards, you can just grab the remixable world, and then you can look at the code in it. You probably will need to set up your own WPVs, though. I'm not sure if they will show up in the remixable world or not. So what are WPVs? They're persistent data that is stored with your world. So they're like PPVs, but they're not owned by any particular player. They're owned by the actual world itself. And they can be accessed at any time in any instance, regardless of what players are there. They can be changed at any time by any instance. And this can cause problems. So just remember, like, if you have a popular world, you might have like 5 or more different instances of that world running at exactly the same time with different people in them. And if those different instances are trying to change these WPVs at the same time, mayhem can ensue if you're not careful. So we'll talk about how to deal with that in a little bit. So there's two types of PVs, just like PPVs. There's a number type and there's an object type. The object type is just a serialized JSON string, just like PPVs. It is a 10 kilobyte limit per variable, just like PPVs. And if you have a lot of data you're trying to store in one of these object variables, you might want to consider using the compress and encode and decode and inflate APIs to try to cram more data into that 10 kilobytes. Probably not as much of an issue with PPVs because that's just per player, but now with the WPV, it's for the whole world. And it's possible you could accumulate more data since it's one variable shared in the whole world among all of the players. So these compress and encode and decode and inflate APIs could be useful. They're organized into variable groups. They can be in the same variable groups as existing PPVs. They're created very similarly to PPVs. They have the same limits as PPVs, 150 per variable group. Here's an example of like what the dialog looks like for creating a persistent variable. You basically enter the name, the type, or name type is the object. The one difference with PPVs is that with world persistent variables, you can set its initial value. You can say this is going to have an initial value of, say, 10 for this number one, or it's going to have some JSON object for an object one. So that's super useful. You can't do that with PPVs. And additionally, you can change the value of a world persistent variable later in the desktop editor. You just need to be aware that that change is going to take effect immediately across all of the instances, including published instances. So just be, exercise caution. Make sure that when you're changing that, any one of your WPV values, you're changing it to something that's going to work sanely for all of your published worlds. How do you read WPVs? So there's sort of confusingly, there's two ways you read them. One of them is the get APIs, and the other is the fetch API. So the get APIs are available. You get the result immediately. It's a synchronous call. It might be slightly stale because it's getting whatever the cached value is. And that value is cached at world start, and it's updated periodically through when you do other operations, but it's not automatically updated. So like you have to do something to update the cached value. And there's two APIs for this. There's get world variable, which gets the object type variable values, and there's get world counter, which gets the numeric counter type value. The other is the fetch API, and this is not a synchronous API. This is going to be asynchronous. So there's a little delay before you get the actual result back. So you'll need to like request it, and then you'll get the answer a little bit later. So, and this one gets the current latest value across all the world instances. So this is the absolute most up-to-date value. It returns promise that's fulfilled when the latest value is available. And when you fetch this world variable value, it's going to update the cache as well. So like once you do one of these fetches, then if you do a get, you're going to get an updated cache value from whatever you fetched. And so you can fetch a world variable either for object or numeric WPVs. It works for both kinds. You know, the object ones will return an object, and the numeric ones will turn a number. So that's the reading part of WPVs. We didn't talk now about the concurrency problems that are around having multiple instances in different worlds changing WPVs at nearly the same time. And if you're not careful, you can lose data. And so I'm going to walk through like an example of a problem that could occur if you had a very naive implementation of how you were updating world persistent variables. So let's consider this. We have this example, like there's this team energy numeric value that's, you know, shared across world instances. And like there's two worlds, there's world A and there's world B, and there's players in both worlds at the same time, and they're playing the game. And these players are updating the shared team's energy value that they both need in order to play the game. So let's imagine, so like when the world starts, like the first thing happens at world start is that each world does a fetch of the WPV storage, and they get the current value at world start. So they're both going to have a cached value of 50 energy. Then sometime later in world B, somebody uses 25 units of energy from the team. So they subtract 25 from their energy value, and then they store, like now there's 25 left, and they store that into the storage. And that store is now traveling over the network to go to the server where the WPV storage happens. A little bit later, somebody in world A purchases 50 energy units for the team, and they update their value from 50 to 100, and then they store that, and it's traveling over the network also to the WPV storage. And for whatever reason, even though this one subtracted the energy first before this one added it, the events arrive slightly out of order because of network latency or something at the storage location. And the one from world A arrives first. So it sets the energy to 100 because that's what they said. Then a little bit while later, the value of 25 arrives from world B. And so it sets the storage 25 as the latest. So 50 units of the team energy just went missing, like you lost data. So this is the thing you need to be careful of when you're dealing with concurrency in multiple systems, updating things simultaneously without any sort of locking involved. So this is the concurrency problem with WPVs. We have solutions for that. So first one we're going to talk about is the counter increment APIs. So these only work with numeric PPVs, and it will read, update, and write the value of that numeric WPV in one single operation. You can only change it by an amount. It can only give it a delta up or down. It can't set it to any specific value. And it is an asynchronous operation. So like you can say like add 5, and then a little while later, it will give you the result of what adding 5 was to the current latest WPV value. And so this API is the increment world counter async API. You give it the key and the amount. The amount can be positive or negative. You can go increment it with a positive amount, you decrement it with a negative amount. It gives you a promise that will have the new value. And also, after you do this increment, it's also going to, as a side effect, it's going to update the cached value for your world. Unfortunately, currently, there's no way to reliably set a numeric counter to a specific value via scripts. We're going to talk about the object WPV set API. It doesn't work. It just fails with an error. It ought to work, but it doesn't. So I would recommend upvoting a feature request for this, because you really do need a way to like be able to say, no, exactly, I need this counter set to a certain value, because maybe it's like hit points or something like that. And like there's some shared mega boss that people in different world instances are fighting against, and you want to set its hit points to exactly 100. And then, in all the different worlds, people will chip away at it by incrementing the world counter async with like -1, to decrement it all the way down to 0. And then when it gets to 0, then everybody wins. But you need a way to reliably set it to 100. And currently there's no way to do that. So just be aware of that. One of the shortcomings of this API. So this is going to solve the concurrency problem for our energy storage example. So same example as before. There's this energy being stored of 50 in the WPV storage. At world start, they both fetch and they both get their cached value of 50. And then the same thing is going to happen as before. World B, someone's going to use 25 of that energy. And then they're going to increment it by -25. So they're not actually saying, hey, I want to set some particular value in the WPV. They're just saying, I want to change the value in the WPV by -25. Then a little while later, someone in world A purchases 50 energy, and they're not setting a value. They're just saying, I want to increment that value by +50. And so again, just like before, this +50 comes first. It takes the 50, increases it to 100, returns result. So world A now has the updated energy of 100. And then slightly later, this increment arrives late, but it then minuses or subtracts 25 from 100 to get 75 and returns this result to world B. So he now has a 75. So no energy was lost here. Like that 50 energy that just vanished into the ether is not being lost in this example, because we had the 50, then we add 50 to 100, then subtract 25 to 75. So, or if we had 50, we minus 25 to 25, and then we added 50, we'd still get back to 75. So no energy was lost. The only thing that you should just sort of be aware of here is that these two worlds have slightly different views of the remaining energy, because their cached values can be slightly out of date. And I mentioned this earlier, is that the cached values might not be the latest values, but they're the most recent values that this particular world instance heard about. So does anybody have any questions about like exactly how like the increment API solved this concurrency issue for us with this simple shared energy team energy example? I don't see any questions about that. So I'm going to, what is the expected delay? It's pretty fast, but I mean, it could be, like a second or something like that, because it's basically a network communication from, this increment is being sent over the network to some server, and then that server has to do a tiny, tiny bit of work and then send a network message back to you. So it might be like, plan on like a second or two at most of delay from when you say do something to get a result. It's probably a lot faster than that, but like it's definitely not instantaneous. It's not something that you can get the value of and then use in your very next line of code. You're going to have to like deal with promises and async await and things like that in order to get the value. So I'm going to jump forward to talk about object variable update. So that was what we were talking about, was the numeric counter update, where you can increment or decrement a counter. So object variable update, basically you're just replacing the whole JSON object that's being stored in the WPV all at once. And there's two versions of this, and it has this really long name. It's called set world variable across all instances async. It takes the key, it takes the value, and then it takes this Boolean, which is allow concurrent override of true or false. So originally we just had this version, which doesn't do any locking, which can lead to data loss, but it always succeeds. Like it's not, the result of this will not be immediately available, but when it does have a promise, and when it returns, it'll be the new latest value for that particular world persistent variable. And it also, like with the increment, it updates the world's cache value. The new API that we got recently is, again, the same name, same signature, but now this allow concurrent override of false means that it no longer allows two different instances to write the same value at the same time. It does this through something called optimistic locking. So again, like the other version, the result of an attempted update is not immediately available. It returns a promise, which, if it's successful, have the new latest. Well, it always has the new latest value and updates the world cached value. But the promise also returns whether the update was successful or not. So whereas this one always succeeds and it always overwrites the value, this one might not succeed and it might not overwrite the value. It always returns you what the current latest value is, but it might say, oh, your thing didn't succeed, and you might have to try again. So, if you're really worried about data loss, you probably almost always want to use this one, because this one is going to prevent you from accidentally overwriting data where multiple instances are trying to write to the same WPV object variable at the same time. So, I threw out this term called optimistic locking. And what is that? So basically, it's really simple. If no one else changed the value since the last time you fetched the value, you get to update it to a new value. But if somebody else changed the value since the last time you read the value, your update does not succeed. So it's sort of optimistically hoping that no one's changed the value since the last time you read it. And if it's so, it just like it succeeds and everything works smoothly. And that's usually the case. I mean, if you have some use case where you have a lot of people updating the same value at the same time, I think you should ask yourself whether you're doing something sane or not, because that kind of heavy data contention is going to slow down your game. So usually, in most of the cases, there's not a lot of writing to WPVs or PPVs for that matter going on. So this is a pretty efficient, optimistic locking is a pretty efficient approach if updates are infrequent. So yes, so the idea is that what happens is that the promise is not rejected. What happens instead is the promise is always fulfilled with both of these, but the promise in this second case with allow concurrent override of false will have a Boolean of success in it, which will be false. So you just need to always check the promise that's returned when it's fulfilled for this version, the one with allow concurrent override of false, and check the success code. If the success code is false, it means it did not update. It does always return you the new value. So you'll learn what the current value is, but just know it's not your value. It refused to write your value. And then you're going to have to try again, and I'll show you an example of this on the next page. Is there any other questions that people have about optimistic locking and why it's the right solution here rather than some more heavyweight kind of locking you can do? Like for people who are familiar, there's things like mutexes and semaphores and stuff like that. And it's like, we don't have any of that kind of stuff here. You don't have to deal with any fussing around like that with that. It's just optimistically assuming that everything is going to work out. And then if it doesn't, it goes, oops, it doesn't work out. And then you have to do some work. So one of the question is, if it fails, can it retry, or do we get a fail result? So we script it to retry. Yes, you get a failure result and you have to script it to retry. It does not automatically retry. So I'll show you some examples of that in a moment. So here's sort of a step-by-step flow through an optimistic locking example. So in this case, say we have a team that has like the shared power-up, like power-ups of A and power-up of B and a power-up of C. And the different teams, or maybe they're in different worlds, but they share the power-up list, and people in each world are like adding new power-ups to the shared power-up for their team. So initially, the power-ups list has just power-up A in it. So when worlds A and B start, they both are going to fetch and cache the current value of power-up list, which is going to be A. And then a little bit later in world B, someone purchases power-up C for the team. So they're going to like take power-ups of A and they're going to append C to that list. And then they're going to store this into the WPV using the optimistic locking API, the one with the allow concurrent updates false. And then a little bit later, somebody in world A purchases power up B for the team. And so they take A and then they add B and they store that into the world persistent storage. And then for whatever reason, because there's networking, latency or something like that, even though this one did the store first, before this one arrives first at the server. And so the server is going to say, okay, your cached version of power-ups had A in it. The latest version of power-ups is A. So the cached version matches the latest. So we're going to take your value. We're going to say, okay, B is the new thing. This is the new latest. And I'm going to send you some result back. A little bit later, this sort of late arriving A comma C power-ups arrives. So here it goes, okay, the latest is A comma B. Your cache version is A. Your cache does not match the latest. So no, we're not going to accept your thing. The power-ups is going to remain the current latest value, and we're going to send you a failure saying, nope, we didn't take your thing. So world B is going to get this failure. They're going to get the new value, though. When they get that failure, they're going to get the new latest value, and they'll now have that in their cache. So they now know it's A comma B. So they need to reapply the purchase of power-up C to their cache version. So now they have A, B, and C, and then they're going to store that. Try again. So at the WPV storage, they're going to see the latest is A and B. The cached version for world B is A and B. So the cache matches the latest. And now we're going to accept their value and change the latest to C, A, B, and C, and then return a success code. And so this guy is going to end up getting their cached version updated to the A, B, and C. This guy, the success message eventually arrives over to the world A, and they know that their A and B were both, the addition of power up B was added. So their cache version is updated to A and B. Just again, like the issue with the energy being incremented and decremented, these guys ended up with different views of the power-ups. But all of their purchases were applied without data loss to the centralized shared storage. That makes sense? Do anybody have any questions about this optimistic locking event example, and like how this guy's store was successful because no one had changed this central storage since he last read it? How this guy's storage was failed because somebody else had snuck in and changed the central value before his store was applied, but that this store was succeeds because no one snuck in to change the value since this guy last got the latest cached value and changed it to a new value. So I'm going to talk about some optimistic locking best practices. So the way I recommend dealing with the retrying, where you have to script the code, is to create a mutator function and retry within some number of limits or some number of times to try to get the value that you're trying to set into the world persistent variable. Your mutator function should be something like this, where it takes the old value and then it returns the new value. It might be called many times, so make sure that you're not doing anything with side effects. Like, don't only have this function just compute a new value from the old value. Don't have it update any other state in your program because you have no idea how many times it will be called. And so you don't want to have any side effects where you're like changing other variables. It should just be really focused in on just, here's the current old value, and then returning whatever new value you want to have for that variable. So for this power up example, imagine like I want to add this new power up of C. And so my mutator function is going to take whatever the old value list is. And if there is no old value, because I'm the first one, I'm just going to make a new array which has my new value in it. Or if the old value already doesn't have my new value, I'm going to take the old value and I'm going to append my new value onto the end. Or if the old value already has my new value in it, I don't need to do anything. So I'm just going to return the old value. So this is sort of a mutator function, has no side effects. It just takes the old value and then it does some computation to figure out what the new value should be, and then it returns it. And then you would use it sort of like this with, you'd call some function that we're going to talk about on the next screen. Let's mutate world variable function. It says, this is the variable I want to update. And here is the mutator function I'm providing that should be called one or many times, potentially, to try to get the current WPV value updated with my desired changes. So I just want to stop quickly so people understand the concept of the mutator. Sole purpose in life is take the old value, transmogrify it based on whatever it is, so you get the new value, and then return that so that it can try multiple times to try to apply your change to the WPV object variable. So this is just a sample implementation of what that mutate world variable function could look like. We'll take, the key for the variable you want to update. This is that mutator function, maybe it's some default number of retries. And basically what it's going to do is it's going to get the cached world variable for that key, the old value. It's going to call the mutator with that old value to get the new value. And then it's going to call this asynchronous set world variable with don't allow concurrent overwrites of false. And that's going to give us some result. So this will potentially take a little bit of time because this is an asynchronous function. It returns a promise, but eventually we'll get the result. And if it was not successful and the error was concurrent update and we have some retries left, do it again. So it'll get the world value, which should now be, this cached value will now be updated because when we called the set, one of the side effects of the set is that it's going to update our cache. And so when we call the get here, we're going to get the new value. And we apply our mutator again, try to call the set again, check the result, and just keep going around this loop until either it succeeds, we get some other kind of error, which is not a concurrent update error, or we run out of retries. And then at the end, we're just going to return whatever the result of the last set world variable across all instances async was to the caller. So this code is in the remixable world, so you don't have to copy this off the screen. These slides will also be available shortly in the forum. I'll make a forum post and I'll stick a PDF of these slides in there. So you can just grab this code either from the slides later or from the remixable world. So last topic is, as we saw in the examples for both the increment numeric value and the set object variable async, is that sometimes you end up with cases where the different world instances are slightly out of sync. They haven't got the very, very latest data. There's no events that you can subscribe to find out when that's happened. It would be nice if there was an event that got sent automatically, which is like, hey, this world variable changed, so that you could then fetch the new value and know that you were close to up to date with the latest value. So maybe upvote a feature request on having some sort of new broadcast event when WPVs change. That would be nice. So in light of that, what you're going to have to do is you're going to have to poll. So on some interval, you just got to call the fetch world variable async API for each WPV that you care about being up to date. You can do this for counters and object variables. You can both use fetch world variable async for both of those. You don't even really need to check the return code of this. It's going to update the cached values. So this will just keep your cache values up to date, and then you can use those get APIs that are synchronous, and they'll just pull the latest cache values. So you might just have some process in your, some interval timer in your world somewhere that's just calling fetch world variable async on all your WPVs every minute or something like that. And then everybody else just uses the synchronous get APIs, and they get something that's within the last 60 seconds up to date. So some shortcomings to this, your local instance might be slightly out of date. It might be operating on some slightly old information. But if you're going to be using the atomic increment or the optimistic locking for object variables, you're never going to lose information. It's just that you might have some cases that are not quite perfect since we don't really have transactions in the system. But you won't lose data. You might have some things that are like not exactly perfect in a couple of cases, and we'll talk about one of them in just a minute. But this is sort of the best approach we have right now. Just be aware that there are some undocumented rate limits on using WPVs, and I don't know what they are other than that they're the default. So definitely if you store too frequently, you can hit the rate limits. I'm not sure if there's a rate limit on fetches. I couldn't seem to get an answer out of anybody on that. So just be aware that you definitely don't want to do stores in a tight loop. You don't want to do it every frame for sure. So just be judicious about like choosing what rate you're going to do your polling. Is there any questions? Should we put a delay on the async WPV write mutate attempts? Yeah, so if you have some use case where you think you need to write WPVs like every frame or something like that, like just rethink your whole approach because that is definitely going to hit the rate limit. And why are you trying to update things that quickly? Think about how you can design your game so that you don't have to like do so many writes. I would maybe, if you do have just a lot of writing that you need to do, I would maybe have some sort of batching system that, you know, in your world, like writes go to some centralized location and then it writes them periodically. For the reattempts, so if you have a concurrency failure on the write, I think you can retry that right away. The other kind of error you can get on a write is a rate limit error. And so there is an error code. If you try to write too fast, your set might return failure and the error code will be rate limited. So that's definitely a sign that you're trying to do things too quickly. If you ever get a rate limited write error, you should definitely set a little timeout and not try it again for, you know, maybe a second or something like that to make sure you let the system cool down and you don't get rate limited again because you don't want to keep like pounding. I have no idea what the rate limit is. I asked and they said it's the default. And it's like, okay, what's the default? And it was like, I have no idea. So I don't know what the rate limit is, but there is one. And if you hit it, you'll find out. So maybe that's something to experiment with. Try writing with increasing frequency until it doesn't work anymore. And then we'll know what the rate limit is. So now I'm going to just talk about two examples. There's a limited run clothing sale. This would be the benefit of this. It's an exclusive clothing. There's only 50 available. So increases urgency of your players to get it before it's gone, bragging rights for your player because they got limited run clothing. And maybe you can charge more for this because it's scarce. So those are some reasons why you might want to do a limited run clothing sale. An implementation, how this is implemented is just a numeric counter WPV. We initialize it to 50. When a player successfully purchases the clothing, just increment it by -1. When the WPV reaches 0, put up a sold out sign and like disable the IWP selling. And then also every 10 seconds or so, just asynchronously get the current WPV count. So you're kind of learning about sales happening in other instances. This is one of these not perfect cases because in the last 10 seconds, you might oversell your item by a few people. If, you know, people are really quickly buying it in a lot of instances, they might subtract into a negative value and you might oversell by a couple. But, you know, if a few extra people, if you sell 53 of your 50 run clothing, you know, no one's going to count all the individual people and make sure that you exactly did it right. So you're probably okay. So this is an example of this limited run clothing. And you'll be able to get this in the remixable world. It has a bunch of variables like that prop that you need to set, like the WPV, you know, the SKU of the clothing you're selling. This is some output text where it sets the status. This is the IWP seller gizmo that we're going to hide when it's sold out. This is how frequently we refresh to get cross instance purchases, defaults of 10. And then this little test button is just to test purchasing so that I don't actually have to go through the whole purchase flow for this demo. So listening for item purchase complete. And this test purchase is just like faking an item purchase complete when they press the button. So like here, when it starts, it's just going to get the current items remaining. It gets us out of the cache because this is world start. So the cache is refreshed right at world start. So this is the latest value. It does a little update of its UI to say how many items are waiting. And then every 10 seconds, it just does a fetch world variable async to like do the asynchronous slow fetch of the number. And then it updates the state with however items are remaining now. And this also updates the cache. When someone finishes purchasing it, if it's the matching SKU and they successfully purchased it, then this is where I'm doing the increment world counter async with a -1. This is where I'm subtracting one from that world variable. This is an asynchronous operation, a promise. So I await the result. And then this is what after I decrement by 1, this is the new items remaining, and then I update my state. And my update state is really just, if there are items remaining, I say there's so many items remaining. Otherwise, if there aren't any more items remaining, I say it's sold out. And as a hack, I'm just like moving the seller gizmo like underneath the world to -100 to like make it so you can't buy it anymore. An example of this in operation. So this is the world that is available as a remix. Here are my variable groups for WP workshop. So this is the item remaining. It's a number world variable. You can see here I can change the number. So it was 5, I can set it to 10, say like, now there's gonna be 10. So this is, again, I was just reminding you that, okay, when you hit save, this is gonna be immediately effective on like all of the instances of your world, including the published ones. So just be aware that that's something you wanna do. That's right, so now it's updated. And then if I jump into this world, so if I jump into this world and I walk up here, so I mean, I have this item for sale. Unfortunately, I can't actually buy anything because of the desktop editor, but that's why I have this test purchase button. So you can see it says items remaining 10. So if I purchase this, all right, 7, 6, 5, 4, 3, 2, 1, boink, sold out. And then as you see, like the IWP gizmo here is gone because I just basically moved it to -100 so that you can no longer buy it anymore. So the other example that I have that's using the object WPV is a custom leaderboard. So this leaderboard is very dumb looking. Like I spent 0 time making it look nice. You can make your own UI, but it lets you show and read your top 100 player scores. And you can get the values of your top 100 players even when they're not in the world. It doesn't require them to be in the world for you to read the value. And when a player enters the world, you can, if they're in the top, you can grant them a special bonus because you can read who's on the leaderboard and what position they are in the world. You can edit the leaderboard to remove cheaters, even if they're not in the world. And then you can reset the leaderboard on your own schedule. You can just there's an API you can just call to reset it whenever you want. So some useful features that you can't do currently with leaderboard gizmo, but you could do if you built your own. I made it limited to 100 players because I'm pretty sure I can fit 100 players into a 10 kilobyte WPV. So that's why I made it 100 players. So it uses an object WPV, which is just containing an ordered list of all the player names and their scores, using optimistic locking and a mutator function to insert or remove players from the score list. For clearing it, it doesn't use optimistic locking. It just uses concurrent override true because like we don't care if there's data loss if we're clearing everything, so it just clears everything. So it makes it slightly more efficient when you're clearing to just like ignore data loss and just clear everything because you mean to lose data, you're clearing it. And then it also polls every minute or 10 seconds or something to get scores from other instances so that you can keep your leaderboard in your world up to date with changes to the shared world persistent variable leaderboard as other players in other instances are updating their scores. this one doesn't have any less than optimal approaches other than the leaderboard might be slightly delayed in updating, but it's never going to lose data. It's never going to misorder people. All of the data integrity should be maintained with this particular implementation. So looking at the leaderboard, so this is the code for it. It comes in two parts. It has a leaderboard service, and this is just a singleton that runs on the server in your world that does all of the leaderboard things. It has a bunch of events that it responds to so that people on local scripts can update the leaderboard by sending network events to the leaderboard. Other things that are on the server can access it as a singleton using get instance to just get directly at the leaderboard service. So here it is listing to all of its events. It syncs the leaderboard on start. Syncing of the leaderboard is just, fetching the world variable for getting all the leaderboard entries, and then updating the cache leaderboard is just sending out a local broadcast event to all the UIs to say, hey, this is the current leaderboard value. It has an API for setting the score, which is using a mutator right here. This is all the mutator function right here that is taking the current value and then adding a new value for that player. There's one for removing a player's leaderboard score, which again has a mutator that just finds that leaderboard's entry and removes it from the score. There's a way to get the player's score, which just is going to use, this has an optional refresh to get the very, very latest data or to use the cache. So the cache will be instantaneous. The fetch will be asynchronous. Get the top players, reset the leaderboard. And then this is that mutate world variable method I talked about in the slides. This is just an example of it in action. And then it has a leaderboard UI, and this UI is all this guy does is he just listens for these cache updates from the leaderboard service, and then he just, redraws his custom UI based on a dynamic list gizmo. There's also like a little tester thing in here, which basically is, calling a bunch of methods on that leaderboard singleton to make it do things, to just show it in action. And then go over to our world. So here I have, I'll just jump into the world here. So here are these buttons here on the bottom. These are just ways to force certain methods to get called onto the leaderboard service. This leaderboard here is listening for updates from the leaderboard service. This other leaderboard here is trying to simulate a leaderboard in some other world where it's not listening for leaderboard updates. This leaderboard over here only updates through periodically every 10 seconds or so, polling the WPV to find the new values. So right now the leaderboard started up and it has 2 players in it. So you can I can get my player value and there's my score, it's 25. I can get the top players, it's gonna go list them. I can remove myself and it immediately removes myself from this leaderboard. This one takes a little bit of time to update because he's polling. And add myself back, immediately adds myself back to this leaderboard. This leaderboard is going to take a little while because it's polling. This is like the leaderboard acting like the leaderboard in the other world. And of course I can clear the leaderboard, which instantly clears the leaderboard in this world, and then this other leaderboard in the other world asynchronously, then we'll find out about it when on its polling interval. So yeah, so this just a very simple example. I mean, this is going to be a remixable world, so you'll be able to take this, take it apart, do what you want to do with it. I would recommend that the leaderboard service, you probably want to use pretty much as is, which is this first part of this file. But you might want to make your own custom leaderboard UI, which looks a lot better than the one I did, which is just a really simple scrolling list. This is the part you probably will want to spiff up and make prettier. So that's the end. Store all the things. These are some resources that you can look at in the slides when I publish them in a few minutes on the forum. These are just some learn site documentation. And this is the API for position storage on the learn site. And then This is the template world that I just showed you that you can take and remix. I should call this is actually a remixable. I call it template world. This is the remixable world that you can go and grab and use to see how all this works. Hope that was educational and informative for everybody. And thanks.